Welcome to this month's ABC UTC monthly webinar. My name is Mary Lou Rawls-Newman. I'm Director of Technology Transfer at the ABC UTC and will be moderating today's webinar. I'll be assisted by Ali Javed, PhD student at FIU, who is managing the web room. Toward Azizi Namini, Director of the ABC UTC, sends his regrets for not being with us today. I'd now like to turn it over to Kathy Kroll, formerly with the New Mexico Department of Transportation and now with the IBT ABC UTC, and coordinator of these monthly webinars starting next month. Kathy?
As we've been discussing for the past few months, the ABC UTC will be transitioning to the IBT ABC UTC next month. FIU and our partners, as noted on this slide, have been awarded funding as a U.S. Department of Transportation Tier 1 University Transportation Center. With this transition, we'll be adding the IBT to our acronym to reflect our added focus on innovative bridge technologies. This is in addition to our focus on the accelerated bridge construction topics. So what do we mean when we say innovative bridge technologies? Some examples are additive construction, such as 3D printing and automation, the next generation nature-inspired and advanced materials, also advanced information technologies, such as AI, ML, and AR. We'll also be delving into topics related to asset management and design specifications. Again, this is in addition to our ABC topics. So you're actually here with us today on a momentous occasion. Today is actually the 150th ABC UTC webinar. The first was in March of 2011. And today, as Mary Lou mentioned, we have over 700 registered sites, which really speaks to the value and the quality of the presentations that we've been giving. So coordinating all of this great content has been a very valuable undertaking. So congratulations and thank you to Dr. Azizi Namini and his team and those who've served on the Technology Transfer Advisory Committee over the years. And a special thank you to Mary Lou Rawls-Newman, who has served as the Director of Technology Transfer since the inception. Her contributions to ABC and really to our industry in general have been truly remarkable. Thank you, Mary Lou. So as we transition the UTC focus, we'll also be reorganizing our team. So Mary Lou will be continuing on, but more in the background and working on the database management and some general support. But you'll be seeing more of me as I take over the coordination of the webinars and the seminars. So if you have any ideas for topics, please send them my way. We're also joined by Bijan Kaligi, who will be focused on the technology implementation. So now I'll turn it back over to Mary Lou for industry announcements.
Thank you, Kathy. And to all participants, I look forward to hearing from you on your ABC projects to include them in the ABC projects database. I'm really excited about moving the database into this new IBT ABC UTC and look forward to getting your projects. Our presentation today features the Utah Department of Transportation's recent £5 million lateral slide replacement of the 1300 East Bridge over I-80 as part of the I-80 and I-215 renewed design build project on the east side of Salt Lake City. We'd like to thank Mark Daniels, Structures Design Manager with the Utah Department of Transportation, for moderating today's presentation. We're pleased to welcome our presenters, Cheryl Hersh Simmons, State Bridge Engineer and Chief Structural Engineer with the Utah Department of Transportation, Logan Julander, Structures Manager with Michael Baker International, and Jim Deschenes, Director of Alternative Delivery with Ralph L. Wadsworth Construction. Also, would like to introduce our Q&A session moderators, Paul Lyles, formerly Georgia State Bridge Engineer and member of our ABC UTC Advisory Committee, and Kathy Kroll, formerly with the New Mexico DOT and now with the IBT ABC UTC. We'll now begin the featured presentation. Cheryl?
Thank you, Mary Lou, for that introduction. And I also want to echo Kathy's thank you to you for your leadership and contributions to ABC. It's our pleasure to be here today to present on one of our most recent ABC projects. Again, my name is Cheryl Hersh, and I'm the Chief Structural Engineer for the Utah Department of Transportation. Today, I'll start off by providing a high-level recap of Utah's Accelerated Bridge Construction Program history. Afterwards, I'll give an overview of the I-80 and I-215 renewed project and introduce the $5 million bridge. I'll then pass it over to Logan, who will focus on some of the critical design considerations, followed by Jim, who will dive into the construction details. We'll wrap up with lessons learned, followed by some time for Q&A. So with that, I will kick it off by first starting with a little history. UDOT's first design build procurement was the $1.6 billion I-15 reconstruction of more than 16 miles of freeway and 142 bridges through Salt Lake City metropolitan area in anticipation of the 2002 Winter Olympics. It was vital that the project be completed before the games started, so the design build team chose several innovations new to Utah to accelerate construction, including the use of precast half-depth concrete deck panels and geofoam film. The project was such a success, finishing both under budget and ahead of schedule, people started to ask why we don't do this all the time. So, as a result, UDOT began research focused on innovations for accelerated project delivery. A portion of the research effort included scanning tours to investigate on a national level what other states were doing. In addition, a series of accelerated bridge construction workshops were conducted to engage industry, educate stakeholders, identify what was needed, and prioritize needs. In retrospect, the engagement of industry was a critical step to the success of the program and achieving the goal of having ABC as a standard practice. It also led to a vision for a family of ABC methods and a plan for a programmatic implementation through pilot projects. Each pilot project set goals based on its specific scope and technology and provided strategic opportunities to gain experience. The first pilot project focused on prefabricated bridge elements and involved a bridge over I-80. The project was a deck replacement using full-depth precast concrete deck panels. It was designed internally by UDOT and constructed in 2003 using design bid build. The limitations of operations offered the contractor incentives and required the bridge to be opened in 7 days. The contractor received the full incentive. In 2007, UDOT used self-propelled modular transporters for the first time to replace a bridge carrying 4,500 south over I-215, not far from the project we'll be talking about today. Since the project involved a new technology, high risks, and a compressed schedule, a construction manager, general contractor, or CMGC contract was used to bring the designer and contractor together early in order to reduce risk and improve constructability. The bridge was replaced in 1 weekend. It took 7 hours to remove the 2 existing structures and 8 hours to place the new structure. In 2009, the bridge replacement for SR 66 over the Weber River was the first project specifying the new bridge be constructed parallel to the existing structure and then slid into place. The original design specified rollers, but the contractor performed a value engineering analysis and slid the bridge on Teflon pads with a hydraulic system. 30 days of closures were allowed in the contract. However, the contractor was able to complete the work in just 7 days. If we fast forward 20 years from that first pilot project in 2003, you can see that UDOT has a robust ABC record with over 200 bridges constructed using a form of ABC. In fact, we stopped tracking several of the elements, like precast sleeper slabs and precast box culverts, noted in the graphic with an asterisk, after 2013, as they were well integrated into our design criteria and specifications by that time. We've established standards based on lessons learned and national research. We continue to evaluate performance and improve design criteria, design details, checklists, and construction specifications to give guidance and ensure consistency. This has been significant for designers, reviewers, construction inspectors, and contractors. With clear expectations, we are able to allow for innovations to meet site-specific goals. Now I want to spend a minute getting everyone oriented. Here's a view of Utah, which sits in the western part of the United States. We'll be focusing on the northern part of the state near Utah's capital, Salt Lake City, which is designated by a star. A significant number of Utah's ABC projects, including some I've already mentioned, have been concentrated on I-80 and I-15, which provides a crossroads to the state. In addition, I-215 forms a belt loop with I-80 in the boxed area. The average annual daily traffic on these key economic corridors provides an obvious reason why minimizing disruptions to traffic is critical, and ABC is a popular solution. Now let's take a closer look at the I-80 corridor near the junction with I-215. This slide shows some of the bridges in the area that have previously used ABC methods and elements, including lateral slides, SPMTs, and prefabricated bridge element systems. In fact, one of the more notable ABC projects happened in 2009. The project included 7 bridges that were moved into place using SPMTs. The space within the loop created by 1300 East on-ramp to I-80 westbound was used for the construction of the bridge superstructures. It was coined the Bridge Farm. The I-80 and I-215 renewed project we're discussing today begins just east of where that project ended. This view of the project area shows the location of the 1300 East Bridge in the upper left corner in the white circle. It also highlights the key items of work for the project, including concrete pavement removal and reconstruction, a new eastbound lane on I-80, 4 replacement bridges, and 2 bridge widenings. The project value was over $120 million and used design build for project delivery. One of the project goals was to maximize mobility during construction. The project used a best value selection with a combination of the proposal technical score and price. The proposer's schedule, user impacts, and road closures impacted the total. There was a maximum closure time allowed for each road with an associated cost per day. For example, 1300 East allowed a maximum of 21 closure days with a cost of $100,000 per day for each full closure. On weekends, I-80 eastbound at 1700 East had a $150,000 cost per day for a full closure, with a maximum number of 12 off-peak closure days allowed. The project was awarded in 2021, and the selected contractor proposed to use lateral slides for the replacements of both the 1300 East and 1700 East bridges over I-80, and a temporary bridge to facilitate phased replacement of the 2 bridges carrying I-80 over 2000 East. 1700 East was slid in 2022, and 1300 East was slid in April of this year. The remainder of this presentation will focus on the 1300 East bridge replacement, otherwise known as the £5 million Utah Bridge Slide. So now we'll look at an elevation view of the 1300 East Bridge before replacement. It's a 4-span pre-stressed concrete girder structure that was constructed in 1964. One thing to note is that UDOT has performed lateral slides with and without the approach slabs attached. For this project, the contractor opted to slide the 1300 East Bridge with its approach slabs. More details on this will be covered as we move on in the presentation. Now, I'll turn it over to Logan.
Hi, I'm Logan. I'll go over some of the design considerations for the bridge, for the 1300 East over I-80 bridge. The 1300 East Bridge was 125 foot wide by 173 foot long with 25 foot approach slabs. The bridge was slid with the 25 foot approach slabs attached. The superstructure weighed approximately 5 million pounds, and some of the material choices that helped minimize that weight were steel plate girders and lightweight concrete deck, sidewalks, curbs, approach slabs, and end diaphragms. This was all supported on full height spread footing abutments. This slide now shows the cross section of the bridge and just how wide it is. The 1300 East Bridge carries 3 northbound lanes and 2 southbound lanes with 2 turning lanes onto the I-80 on-ramp. There's a 6.5-foot sidewalk on one side and a 17-foot shared use path on the other. And as Cheryl had mentioned, the existing bridge was a 4-span bridge that I've highlighted in gray. The replacement bridge is a single-span bridge with the abutments located in between the first and fourth spans, as highlighted in blue. This way, the abutments could be constructed while the existing bridge was in place and in service. The superstructure was slid on the abutment with the approach slabs connected, and the approach slabs were supported at the ends on transition elements that UDOT refers to as sleeper slabs. And I'll talk more about those later. Now, the distance from finished grade to the bottom of the footing is approximately 31 feet. So the spread footings were relatively large and made the clearance between the existing bridge foundations very tight. The existing abutment and pier are highlighted in gray, and you can see the battered piles at the abutment. A temporary soil nail wall, highlighted in orange, was used to retain and protect the existing abutment during placement of the proposed spread footings, but the wall also had to avoid the existing battered piles. Now, due to deeper clay layers and the service condition controlled for bearing pressure, and a few tactics that were used to reduce the forces on the spread footing were the use of lightweight cellular concrete backfill, shown here in blue, and a tall end diaphragm. Not only did the tall end diaphragm reduce the horizontal forces on the spread footing, but it also lowered the top of the abutment stem, which made it easier to construct below the existing bridge. Now this shows the abutment and elevation with the temp support, and a common temporary support for bridge slides are driven piles with a top support beam at the slide plane, as shown here as an example. However, the temporary support for this bridge was essentially an extension of the abutment spread footing. The permanent abutment is shown in blue. Oops. And the temporary support is shown in orange. Having similar substructures reduce the risk for differential deflection between the permanent and temporary abutments. Now this picture shows the same view of the abutments with the superstructure in the final condition. And again, I've highlighted the permanent portion in blue and the temporary section in orange. The approach slab was supported on the temporary shoring that can be seen in the background of this picture. Now, Jim will go over this more in depth, but in this upper elevation view, it shows a rough diagram of the bridge slide. This is looking at the abutment with the bridge in the temporary location next to the existing bridge. For the bridge move, threaded post-tension rods passed through the end diaphragms and were anchored at each ends in these end blocks highlighted in green. Hydraulic jacks were placed at the right end to incrementally jack the superstructure into place along the threaded rods. And after the superstructure was slid into the final location, as shown in the section below, the temporary abutment highlighted in orange was removed, and the remaining sections of the wing walls highlighted in dark blue were then placed. Now, the abutment diaphragm was designed for different loading scenarios during the slide and in the final condition. The orange blocks indicate the slide or skid shoe. locations that the bridge was supported on during the move, and this picture shows the slide shoe used for this bridge. The blue rectangles are the final bearing locations, and it was decided to use 2 slide shoe locations so that each shoe would have constant pressure during the bridge move, as opposed to several locations where you could have a shoe take more load than the others or have no load at all due to minor variation in the slide surface. This, however, placed the slide shoe locations 69 feet apart, which produced some large positive and negative moments in the end diaphragm. So the end diaphragm was essentially designed like a pier cap. This is another reason that the tall end diaphragm was helpful in design. And this section shows that 11-foot tall end diaphragm with the additional reinforcing below the girder and in the deck. You can see the 2 conduits that the threaded rods pass through highlighted in orange. After the bridge slide, there was a 1-foot 6-inch gap between the top of the abutment stem and the bottom of the end diaphragms. The picture on the left shows that gap with the actual bridge. Now, in order to close this gap, a 3/16-inch bent plate was attached to the end diaphragm, as shown in green. This provided allowances for temperature movement and was sufficiently rigid to retain the lightweight cellular backfill. Now, the approach slab was connected to the end diaphragms, and at the opposite end was slid on these precast sleeper slabs, as shown in this section. One concern with sliding the approach slabs with the bridge is that there is only a 2-inch gap at the ends for temperature movement. Now, because the bridge is 125 foot wide, if the bridge were to rotate less than 1 degree, that 2-inch gap would close. So in order to provide additional longitudinal clearance, a section of the sleeper slab stem was cast after the approach slabs were placed. And this section shows the end of the approach slab with the precast sections of the sleeper slab shown in blue, and the orange section is the post-installed portion of the sleeper slab stem. So this provided 5 inches of clearance from the end of the approach slab to the post-installed stem bar reinforcing during the slide, and then approximately 1 inch of additional tolerance for setting the joint after the slide. Additional clear cover to the top reinforcement was provided to allow for grinding to account for any vertical differences. Now, often bridge slides have unconventional details, but at the end of the day, we want the bridge to look like one homogeneous structure. It takes some forethought and design to help the bridge look aesthetically pleasing. A couple of aesthetics considerations for this bridge slide were the form liner, post-slide installed wing wall sections, and shear keys above the slide plane. Also incorporating a 7-foot by 7-foot city logo on a wing wall that could be seen from I-80 below. Now, the wing wall with that sign and the figure on the right is perpendicular to the abutments and other wing walls, so it would not be feasible to slide the bridge with the wing wall attached. So this wall had to be installed post-slide, along with any component above the travel path of the bridge. This led to many form-saver rebar couplers, rebar extending out of the abutment where possible, and then afterward, careful removal of the temporary supports. So after much planning, detailing, and careful construction, the final product was a great-looking bridge. And now, Jim will discuss some of the construction aspects of the project.
All right, good afternoon. I'm Jim Deschenes with Wadsworth Construction. My presentation is going to be focused around a time-lapse video of the 48 hours of the bridge slide itself. But I wanted to start out by saying the bridge slide was not the ultimate goal for the project. The goal for the project is really to provide a long-lasting maintenance-free bridge for UDOT. The purpose of using the slide was to replace an existing structure with the least impact to mobility as possible. That being said, there were a number of factors why a bridge slide made sense for our team in this location. One major factor is we've executed 10 similar bridge slides, most of them with UDOT and most of them with Michael Baker design engineers. That experience from all parties is critical in achieving the project goals and providing a high quality, low maintenance structure. Another factor is there was only a small profile raise from the existing roadway. Profile increases of more than 12 to 18 inches significantly impact the amount of roadway approach work that takes more time than the bridge slide itself. This bridge has basically zero skew. Let that catch up. Which made it really easy to control the alignment and design the slide system. Another factor is there's plenty of available space to build the bridge in a temporary location before executing the slide. Being able to build the bridge in a single phase in a temporary location has many advantages, including only closing the freeway for one night to set all girders instead of a multiple night closure for each traditional phase construction phase. Other advantages include no cold joints at the deck closure pours and an increase in safety for our crews as they are physically separated from traffic. A major task in any bridge slide is the demolition of existing bridge. And as you can see, the new bridge was only 2 feet away from the existing bridge. The first step for this bridge was milling the existing overlays. This was done while freeway traffic was still open beneath the bridge. Milling allows us to recycle the asphalt and reduce the amount of material we have to process when existing bridge is demolished in place. For this existing 4-span bridge, we saw cut the deck and removed the end spans without closing the freeway. The end spans were short and relatively light. The large sections were hauled off to be processed in our yard, saving time to demolish these spans once the freeway was closed. A key component of the bridge slide is having space to build the new substructure under the existing bridge. In this case, the new abutment and slide surface was under the end spans of the existing bridge. A controlled removal of the end spans allowed us to prepare and protect our slide surface and install the post-tensioning rods we used to move the bridge before demolition was complete. As you can see in the video, we left one section of the end span in place to access the demolition of the main spans. The analysis of the existing structure and the demolition plans were provided by RLW engineers. The actual demolition is one of the more action-packed nights of a bridge slide and makes for great video, but the reality is it's really a long night of noise and dust. We'll speed up through the demo here and use this opportunity to talk about our schedule. Our planned schedule was to close 1300 East on Wednesday evening at 4 p.m. As we just saw, we started with overlay and milling the end span removals. We also started roadway approach work and drainage utility work. We closed I-80 in both directions on Friday night at 10 p.m. and began demolition of the main spans, the longest activity duration of the weekend. The actual bridge slide was scheduled for 6 p.m. on Saturday and was planned for 10 hours to be completed by 4 a.m. Sunday morning. The remaining tasks were final cleanup of I-80, resetting the highway barrier, and a bridge inspection by UDOT before we opened the freeway to traffic. Conservatively, we had planned on an opening of Monday morning by 6 a.m. We started the actual slide about an hour early at 5 p.m. on Saturday and finished in just under 7 hours. We were able to reset the barrier, do a partial inspection, and open I-80 by 3 p.m. on Sunday. The total freeway closure was just under 42 hours. Here at the end of the demolition, you can see that utility and roadway work is underway at the ends of the bridges. Moving down to the freeway level, this view shows where the new abutment is constructed between the existing pier and the abutment of the existing bridge. And from this view on Saturday morning, you can see more of the elements critical to our bridge slide. From this angle, you can see the new abutment and its location between the existing pier and abutment, and you can also see the new abutment and slide surface being protected by timber and plywood as we finish the demolition. One critical component of our bridge slide was sliding the approach slabs along with the bridge. UDOT uses sleeper slabs at the ends of the approach slabs as Logan described earlier. Therefore, before we slid the bridge, we had to set and level precast sleeper slab sections. Here we are setting the precast sleeper slab sections, which sets up our transition to the actual bridge move. We'll take a break from the video here to talk about some risk mitigation we implemented on the project. The first mitigation was having a number of pre-activity meetings. As you can see, we had a number of people involved and we had to coordinate our efforts. Some of our crews had been present during past bridge slides, but we really needed to get everyone clear on their roles and responsibilities for this particular slide. Survey was also critical to a successful bridge slide. We performed multiple surveys of the slide surface, slide shoe elevations, and final pedestal elevations prior to sliding the bridge. We also performed deflection analysis of the end diaphragms as the support locations were different during the slide than they were in the final position. Although deflections were small, they were measurable, and we needed to have a complete picture of the as-built bridge pedestals and as-built abutment bearing location elevations to make sure that they would work with the final bearing pads to achieve the critical vertical tolerances. Another aspect of the move, as you will see in a minute, is that when we were moving the bridge, the workers at the abutments placing the slide pads for the bridge and monitoring the progress are under the approach slab and out of sight of the jack operator who is up on the deck controlling the hydraulics. To overcome the line of sight and communication problems, we set up a series of video cameras and had a monitoring tent on the bridge. As you can see in this photo, we had cameras at the leading edge of the bridge deck looking down at a survey stake and metal tape at the center line of the abutment. We also had cameras watching the hydraulic jacks. The hydraulic jack operator could watch the bridge move longitudinally and laterally with every stroke of the jack. This was critical to keep the bridge aligned during the move. Moving on to the actual bridge slide, we used two 200-ton hydraulic rams, one at each abutment. The bridge was slid on PTFE bearing pads lubricated with dish soap. Each abutment was slid on removable slide shoes. Once the bridge was in place, we lifted the bridge, removed the slide shoes, and set it down on the final bearing pedestals. Each abutment sits on laminated elastomeric bearing pads in 5 locations. To accelerate our schedule, we started moving the bridge before demolition and cleanup was complete. One key aspect of our move was sliding the approach slabs with the bridge. One innovation we used to accomplish this was to use PVC catch basins that we could pre-install into the approach slabs. The lightweight allowed us to suspend them from the approach slab using typical pipe hanger hardware, which would not have been possible with concrete catch basins. In this view, you can see the camera attachment frame and survey stake at the leading edge of our abutment. You can also see the steel frame that served as our lateral steering guide for the bridge. I'll talk about that in a few minutes. As you'll see in these next portions of the video, the ends of the approach slab, the sleeper slabs, the reaction blocks, and the PT rods that were used to move the bridge. The critical alignment area is between the approach slabs and the sleeper slab stem wall. It's critical to keep the gap constant and not bind the bridge against the stem wall. In this case, as Logan noted earlier, we created a larger gap during the slide by holding back the stem wall concrete. This provided an extra 2 inches of lateral tolerance during the slide. This view is from the south abutment showing our leading edge survey stake along with the PT rods and reaction blocks we used to move the bridge. Moving under the bridge, you can get a good view of the reaction blocks and PT rods. As we pan around, you can see the permanent concrete pedestals on the abutment stem. These are where the final bridge is supported, but as shown earlier, they are not being used as supports during the slide. Coming into view shortly here will be the leading edge and camera setup and a close-up view of the PT rods where they run into the abutment stem wall. The vertical steel section about to appear is the lateral steering guide. Getting way ahead. The steering guide worked well in a few instances where we had to nudge the bridge back into alignment. The guide was not designed to jack the bridge laterally on its own, but rather to work in conjunction with the forward movement of the bridge to guide it back into alignment. Each steering guide had a small hydraulic jack mounted horizontally that could apply pressure to a slide pad mounted to the face of the abutment. By placing side pressure on the abutment, as we move forward, we could guide the bridge back into alignment. The analogy is pushing a car on a snowy road. It would take a lot of force just to push it laterally, but if you use the forward momentum, you can easily move it sideways with less lateral pressure. As we work into Saturday night, you can see the gap between the approach slab and the sleeper slab gets a lot of attention at the end of the slide. Even with the additional joint space provided between the stem wall and approach slab, a 5-inch gap on a 125-foot wide, 175-foot long bridge looks pretty small. This view from down below shows the end of the bridge slide early Sunday morning. You can see the concrete pedestals that support the bridge in its final position. The pigeons approved of the new steel girders with their wide flat bottom flange. After sliding the bridge laterally for 108 feet, about 7 hours, the final position was within a 1/2 inch, both longitudinally and laterally, and within a 1/4 inch vertically. The freeway was open after a 42-hour closure. 1300 East was closed for an additional 3 days as we completed the roadway approach work and paving. This shows our backfilling and compaction efforts behind the sleeper slab stem wall. The even joint space between the stem wall and approach slab demonstrates our pre-work and planning resulted in a precise final location of the bridge. The final closure stats for I-80 were 10 hours to set girders and the 42-hour bridge slide for a total of 52 hours or 3 days of off-peak closures. The original RFP allowed up to a maximum of 12 days of off-peak I-80 closures. 1300 East was closed for 6 days. The RFP allowed up for a 21-day full closure of 1300 East. The shorter durations made possible by using a bridge slide were a major reason for our best value selection on this project. And after the bridge was open, we still had to fill under the approach slabs and construct the final wing walls. We used cellular concrete to fill in beneath the approach slabs and around the PVC catch basins. This move was our heaviest slide to date and most critical in terms of mobility for one of the busiest sections of freeway and cross streets in Salt Lake City. There are a lot of details we didn't have time to cover, but I hope this gave everyone a good overview of how we were able to make this bridge slide a success. Since the first bridge slide in 2009, UDOT designers and our builders have continued to develop and improve design criteria, design details, and construction specifications specific to bridge slides. And here in Utah, we're at the point now where a bridge slide is considered for just about every bridge replacement, regardless of the delivery method. Thank you. That wraps up my part.
Thank you, Cheryl, Logan, and Jim, for sharing your recent ABC project with our participants today. Great presentation. Love the video, too.
All right. Yeah, I'll just go over a few of the lessons learned. So communication was key to the success of incorporating the slide elements into the design. And this project was design build, so the designers worked directly with the contractor to plan how all the slide details could integrate with the structural details. Those key items being the temporary structure or temporary supports and slide method, either being push or pull, and then adjusting those details to accommodate the different methods. Now, if the project is a traditional or design bid build, the designer makes assumptions of the methods used for the bridge slide. So those assumptions need to be clearly conveyed within the contract documents so that the contractor can know what modifications to make based on their means and methods. Also, for the bearings, communication was key, and there were several different bearing conditions during construction, during the slide, and in the final bridge location. Now, the final bearing locations were not under each girder line as is traditionally seen, and it was found helpful to design for additional construction tolerances than is required by AASHTO.
On the construction side, a few lessons learned. I mean, one was there was a lot of talk about sliding the approach slabs. That hasn't necessarily been done on all of our slides, but it's highly recommended. There's challenges to be overcome to forming and placing and sliding the approach slab with the bridge, but the benefits of overcoming those challenges make it worthwhile. It's better for traffic and it's better for worker safety. Survey and monitoring, again, I think really emphasizing to our crews that good craftsmanship and tolerances matter on a bridge slide is important. That's for finishers leveling bearing pad locations, carpenters building forms, and the surveyors getting accurate as-built measurements. There's fewer opportunities to correct issues through rework once a bridge has been slid into place. So the extra attention to detail, the calculation of deflections, monitoring movement, with each jack stroke, they were all keys to making the slide as accurate as it was. So I think survey and monitoring, very, very important lesson learned on this project.
Okay, and the last lesson learned we have is on a programmatic level, and that's the fact that having clear and consistent expectations makes it easier for those developing, constructing, and overseeing these projects. So for convenience, we provide links to all of the ABC-related information in a single spot on the UDOT website. The link is shown here. And then I'm going to kind of navigate through. This is what that site looks like. And if you scroll down, you'll find the Accelerated Bridge Construction Information section. And then within that section, we have inventory inspection reports, which document observed performance of various ABC details to help us improve performance. Lessons learned reports, which document details from the early implementation. Project highlights, which provide project-specific information and photos on our past projects. And then if you go under resources, There are links to our ABC related standards, including a chapter from our design manual, drawings, including some sample sheets, and checklists. Now, ABC, like Jim mentioned, is considered for every project, and the decision-making tools included in this section have a rating process and a flow chart for designers to use. In addition, we have construction specifications that support ABC, including a move bridge specification, which provides requirements for submittals, monitoring, and tolerances for each type of bridge move. Now with that, we complete our presentation and turn it over to Paul for questions. Thank you.
Okay, well, thank you very much. And great presentation. Yes, the lessons learned and the resources you provide are extremely important. So thank you for presenting those. Okay, now we'll start with the Q&A session. Paul and Kathy. Paul, you want to get started?
Okay, Mary Lou, thank you. And Cheryl and Logan and Jim, really an interesting project and pretty impressive. We do have a lot of people here, and we're starting to getting a bunch of questions. But anyway, I'll go ahead and I'm going to open up with one that was, it came in before the presentation, but y'all really didn't get to see it. It's a new one for y'all, and it says, what was the governing criteria that were used to advance this bridge replacement as a lateral slide?
And I'm going to turn that over to Jim from the contractor side of the design build team.
Sure. This being design build delivery. I'm sorry. A major factor in our selection its overall best value, but the biggest component of that is cost. And in this job, cost was divided into actual hard dollar cost, but also this lane closure cost that UDOT had provided. Cheryl mentioned the $100,000 a day, the $150,000 a day for various closures. And so, like, if you took the full 10 days say 10 days on 1300 East at $100,000 a day, that's $1 million. If you could, and you had to add that to your bid. And if you could do it in just 4 days, that's only $400,000. So you're $600,000 ahead. And really, that's the primary driver of using ABC on this project. But that being said, like I said at the end of my presentation, we consider bridge slides in Utah for every bridge, regardless of the delivery method, based on a combination of basically risk. Is it safer? How much does it cost the public? Quality can be better on a bridge slide. So those are all typical drivers, but in this case, it was primarily cost.
Okay. The second question I have, it's really a design question here, and y'all have seen this one. It says, what design wind loads are applied to the temporary structure, and how are the sliding loads modeled and applied to the temporary structure?
Yeah, so really, the wind loads were pretty negligible load to the bridge, and the temporary structures, especially considering the lateral earth pressure and accounting for that. So those didn't really control much, but we did have to look at the different locations during when the superstructure was in the temporary location, and then in the final location, and account for all those different loadings. And those didn't control as much as the final loading on the bridge in the permanent location. So we had reduced the temporary abutment spread footings considerably to account for that as well.
Okay. We got some questions on the lightweight concrete. Could you look at slide 18? I don't know if you could put that up. See it up though. There it is. Okay, yeah. We got three questions here involving the lightweight concrete. Now you say your fifth bullet down over there on the left: lightweight concrete deck, sidewalk, curbs, approach slabs, and end diaphragms. And the first question here was, can you please detail the benefits of using structural lightweight concrete in this type of bridge construction?
Yeah, so there were two benefits mostly. Was reducing weight for the actual slide, the amount that the bridge was moved, and that ended up being around 655,000 pounds by using the lightweight concrete, and also in reducing the loads on the spread footing abutments to minimize those, that bearing pressure load, to get that to an acceptable amount.
Okay. And this was a design bid build, so y'all, the contractor, y'all were all working together on that. Is that reducing the loads? Is that right? Using lightweight aggregate.
That's true. I think it doesn't. At the end of the day, like Logan talked about, there's the live load component of the bridge design, which really controls most of the structural aspects of it. So reducing the weight is important, but it's really just a matter of the size of the jack. We could use bigger jacks, and those jacks are available. So it's not a requirement for lightweight. I do think from a cost standpoint, lightweight has historically been cost effective in Utah because there are lightweight aggregate sources close by.
Okay.
And that's one of the reasons we use it. Had there been no close by aggregate sources, we probably just would have went with normal weight.
Okay. That's sort of the next question here. It says, does the weight of the structure matter that much for a slide? You said you just get a bigger jack, but anyway, would using lightweight concrete have been that beneficial? It looks to me like maybe the load on the footings was a pretty important thing, like you mentioned. Is that right about getting a bigger jack?
Yeah, that's the jack. And the jack capacity, of course, has there's a couple of factors. Obviously, the jack is rated, say, at 200 tons, but you can really push 300 tons with it. And then the factors of safety we put on, the contingency we put on the weight of the bridge, some live load consideration, some friction factor variability depending on what we're sliding on. So the jack's more than capable of moving two 200-ton jacks, more than capable of moving this 5 million pound bridge. It's really not a determining factor in using lightweight or not.
Okay. The next question here is about lightweight again. It says, what are the benefits of designing with structural lightweight concrete? Meaning, it says ASTM 330. Is that what y'all use? Do you know? And then it says, with the reduction in deck weight would be a benefit. Is that where you got your most reduction with the lightweight?
Yeah, the end diaphragms were also, I mean, they were relatively large, so there was a big portion of that was from the end diaphragms as well.
Okay. How about your sleeper slabs? Were those done lightweight, or did you just do those with regular concrete?
Those are regular concrete.
Okay. Yeah. Okay. We'll move on. There were a few questions here that this is probably more construction. Can you speak to the design tolerance requirements from the Utah DOT, specifically between adjacent slide shoes and any other considerations?
Really, the final bridge tolerances more or less mimic what you would expect for a final, for a regular built-in-place bridge. The tolerances that we worked with were really during the slide, like Logan mentioned. There was a lot of talk about the back of the approach slab and the sleeper stem wall. In the past, when we've slid bridges and they've gotten a little bit out of skew, that sleeper slab will bind up against the approach slab, and then you're kind of stuck. And so we have contingency plans we can back the bridge up, we can tweak it one way or the other. So that's kind of, that's the tolerance we're concerned about. Obviously, the DOT expects this bridge to be really, from a final ride quality standpoint, equal to any other bridge, any other structure they have out there. And so that's our tolerance. I mean, we've done things like Logan said, we left that little portion of the stem wall that we could cast in place afterwards. So if the bridge was off like a little bit of an inch or two, we could make up for that. But really, this bridge had a crown in it, and I don't know if you could see from the video, but it was a little weird because as we're sliding across, the approach slab is, a 1.5 feet lower than the crown. But then once we get into final position, the crown matched up great, and it was pretty cool.
Okay. A few more on the monitoring and in the movement. What kinds of means and methods did you use to monitor any twist, deflection, or geometric discrepancies?
So this subject has gone through a lot of iterations over the years of UDOT bridge slides and setting up all sorts of crazy monitoring methods that really proved to be not all that beneficial in terms of what was telling us what was going on with the bridge. So right now, I mean, it's during the slide, it's supported on forward bearing locations. It's pretty easy to determine the load at each bearing and keep that constant. There is no twist of the bridge. Again, a lot of the survey to make sure that our slide surface and final abutment elevation seats were all level, again, contributed to just a smooth lateral slide of the bridge. We had the leading edge camera survey stake. That was a way to monitor the bridge as we were moving. Our surveyors were out there. We had targets on top of the bridge, and so as we were moving across, they were checking elevations with every step just to make sure we didn't have any weird settlement. But really, there's not a lot of monitoring of the bridge for twist or any kind of weird movements during a slide. I think that's much more applicable to SPMT moves or some other type of ABC method. I'll just say, I mean, these bridges are like big sheets of plywood. Really, that's the best analogy, right? They're not flexible, but they're not rigid. So if one end is an inch higher than the other one, you don't really have any detrimental or structural impacts.
Okay. The next question is, what type of monitoring, if any, was used? This came in beforehand. Was used to monitor the structure during the move. You showed some pictures of that, and you've kind of discussed that. You want to add anything to it?
I just that every time we've slid a bridge, we've done something a little bit better, a little bit different. And this one, with the size of the bridge and it being, the guys just couldn't yell at each other saying, hey, you're an inch this way or an inch that way. We set up that camera system, which really proved to be great. I mean, it was really great. So that's about all I need to add.
Okay, that's good. Then there was a question here about cost. It says, how did the slide project cost compare to conventional construction costs?
So I'll just caveat this a little bit by saying this could be, I could be off by a factor of 4. But in general, when looking at a bridge option, whether you're going to slide it or not, I would take the cost of a conventional bridge and say add $500,000. It's all situational, and obviously the cost of the temporary substructure is a big quantity increase, so that cost is higher. The productivity is about the same. Setting girders, pouring deck is all about the same. I would say the control and the risk is better. We have, we have more control over days we can work. We're not limited to working in a crappy weather day because we committed to, we have this lane shut down. We can not work that day. So there's some cost savings there. There's some design costs that go up a little bit. The details that design needs to accommodate the slide add a little bit of cost, but not a lot. And then user cost is a big, is a big part of this. If the DOT says, hey, this is worth $100,000 a day, then we have $100,000 basically to spend to create the slide. But really the temp structure, the slide mechanism, you saw there was a large number of people associated the night of the slide. Those are all costs. So that's what I typically, when we just look at a big picture, how much would it cost extra to slide this bridge? $500,000. I mean, it could go double that. It could be less than that. So ballpark.
Okay, that's real interesting. We have one question here that came in. Let's see, this is a new question. What is the superstructure depth versus the existing, since the proposed bridge is a single span?
I can get that number and post that afterward, but we did have to account also for the existing bridge had reduced clearance as well, and so there were a few things that we had to do in order to make up that vertical clearance for over I-80. But yeah, I don't have the numbers on me right now.
That's fine.
One benefit was we used steel girders versus the existing bridge was concrete girders, and it was relatively old with regular concrete strength, so it wasn't designed as tightly as this new one. That's for sure.
Okay. No, I was going to ask the question on that. I noticed that the original one was concrete and the new one's steel plate girder. Did you use any exotic steel in it, or is it just regular steel? 50
Just regular. Yeah.
Okay. That's most of the questions that have been asked before the question and answer started. Well, we do have a number of them that have come in. I'm going to ask Kathy to come in and pick up the question and answer period questions. Kathy?
Great. Thank you, Paul. So one question that came in, and this might be in the category of get back to you later, but what is the estimated settlement for the spread footings? Do you have a sense of that?
I know it had to be less than an inch for the settlement. So I know it was yeah, again, I'd have to look that up, but I know it was close.
Okay, great. So an inch for starters, and then we can hone in on that with the posted question and answers. Question for Cheryl, are incentives and disincentives a UDOT standard practice? And what are your thoughts on the effectiveness when they're used together?
It really depends on the project. And so we have a whole toolbox of things we use for the right situation and depending on the project goals. User costs are a typical requirement that we put in, to show the importance to us of mobility for users.
Thank you. There are a couple questions regarding the joint behind the end diaphragm and the abutment. I'm not sure if you can find the slide on that. If you look for that, I'll ask another question in the meantime. So can you comment on how the bearing locations under the diaphragm, rather than traditional bearings under girders, were considered for load transfer from super to substructure?
Yes, so that's a good question, and like I had mentioned, this was kind of designed as more, end diaphragm was designed more of like a pier cap, just because those bearing locations were different than the girder locations, and the depth of it also helped in that distribution of the girder and the superstructure loads over that 11 feet in order to kind of distribute those out. And we placed the bearing locations so that it would be balanced in the final location for those superstructure loads.
Great. Okay, thank you for pulling up that slide. So the question related to that slide is, can you please describe a bit more about the cover at the joint between the end diaphragm and the abutment that protects the bearings from the backfill? Can you please describe a bit more about it?
Oh, okay. That it was it was covered by that steel plate, and so there had been different ways in the past that we had covered up that joint, but the steel plate was a good, robust system that we feel like will last for the lifetime of the bridge.
Is it also covered with a waterproof membrane? Am I seeing that?
Yes. Yes, that is correct. So there is that plate that goes on the back, and then a waterproofing membrane that covers, from it overlaps the end of the plate and comes down, and there's slack here at that area in order to allow for temperature movement so it doesn't rip the waterproofing membrane.
Okay, that sounds great. I know that was a detail that we had lots of debates about at New Mexico DOT too, so it's interesting to see how other people do that. One other question, and I think this is an easy one. The question is, can we get a copy of the ABC decision-making tools? The website link requires permission to view it. Is that true, or is there a UDOT website where all of those links are active?
It should be available for everyone. I'll have someone check to make sure that there's not something blocking it right now. That's not the intent. The intent is it's open for everyone.
Great. So do look back. We'll make sure that those links are included with the question and answer posting. And that is all we have for questions today. Mary Lou, would you like to rejoin us?
Yeah, thank you. Thanks again to Cheryl, Logan, and Jim for sharing your impressive lateral slide project. This is a great project. And for your thoughtful responses during the Q&A, that really helps our participants to better understand the project, so we appreciate that. Thanks also to Paul and Kathy for moderating the Q&A session, and to Ollie for managing the web room, and to all participants for your interest, attendance, and as usual, excellent questions. Kathy, it's all yours.
Thank you. So another huge thank you to Mary Lou for all the work that she's done on the webinars and the seminars to date. I look forward to continuing to work with you. So please join us on October 12th for the first IBT ABC UTC monthly webinar, and also for the quarterly research seminar on October 27th. Thank you for your attendance, and the webinar is now complete.